A fair die is rolled. Let x and y random variables denote respectively the number of rolls necessary to obtain a 6 and 5. Find the expected value of random variable x, the expected value of random variable x given the random variable y is 1, and the expected value of random variable x given that the random variable y is equal to 5. Alright, so the first part is to just find the expected value of the random variable x. Alright, so we will denote it simply like this, as given. And this is equal to the summation from the first trial to the infinite number of trials, right? Because we're gonna infinitely roll the die to see the number of rolls necessary to obtain a 6 and 5. In this case, we just want to find the number of rolls necessary to obtain a 6, right? Because this is what the random variable x represents, right? So for this reason, we're going to use the summation from the first trial to the infinite trials, right? X multiplied by the probability of the random variable x equal to that x, right? So basically, again, starting from the first trial, going infinitely up, we're going to have x multiplying, and what is the probability of the random variable x being equal to x? Well, so we're aiming for the number of rolls necessary to obtain a 6, right? So the number of rolls will be basically the number of trials necessary for the first success, right? So we know that the probability of a failure, right, because in a die there are 6 faces, so there are 5 faces that are failures, right? So 5 over 6 is the probability of a failure. Now, how many failures are we're gonna be expected to have? We're gonna need x trials, right? Because we need to have the x trials in order to have the first success, right? So that means that x minus 1 will be failures, and we raise it to the power of x minus 1, the probability of failure, because each failure is independent of the other, right? Because each roll of a fair die is independent, right? Each time you roll a die, it's independent of the previous roll, right? That's why the 5 6s will multiply themselves, all these failures. All x minus 1 failures have the probability each occurring with 5 6, right? And then the last one, the last trial, which will be the first success, will be with probability 1 6. That's when you first see the 6 being rolled, right? Because random variable x represents the number of rolls necessary to obtain a 6, right? So this is basically what the previous notation suggests for us to use, the binomial distribution, that is. So now we can take the 1 6 out of the notation and basically keep this 5 6, sorry, x comes before that, so x times 5 6 raised to the x minus 1. Now we know that this is going to be equal to what? This is going to be equal to 1 6 being multiplied by 1 over 1 minus this part, 5 6 squared. Alright, and if you want to see how this is done, why this is true, why this is the convergence basically of this infinite series, watch our infinite series and sequences tutorial, the playlist, that is, the separate playlist, where I show how to arrive at this conclusion, right? So now this is equal to what? This is equal to 1 6 over, that's going to be 1 6 squared, right? So 1 6 squared. So that's going to be equal to 1 6 multiplied by the flipped square of this, which is going to be 36 over 1. So that's going to be 36 over 6, which is going to be equal to 6, right? And this result makes sense, because naturally, since you were talking about a fair die, each face has the equal probability of occurring, right, upon each roll. So naturally, since there are 6 faces, you will expect to roll a 6 in 6 trials, right? Because there are 6 faces, so you're expecting to see at least one 6 being rolled when you roll 6 times, right? So this is the expected result. It's good. The second part is conditional now. Now this is conditional, so we're talking about from the first roll rolling infinitely, x being multiplied by the probability of x random variable equal to x given random variable y is equal to 1. Okay, so now what do? How do we arrive at the conclusion? Basically what this notation means is that we will have from the first to infinite we're talking about x being multiplied. So what is this probability equal to? The conditional. It means that we will have the probability of x being equal to x with at the same time y being equal to 1 over the probability that the random variable y is equal to 1, right? This is the conditional probability that you should recognize. So first let's find the bottom. So I'm going to put this as a note. So the probability that the random variable y is equal to y, for example, right? Basically the probability that you will see a 5 being rolled on the yth trial will be equal to what? 5, 6 is the probability of failure. There will be y minus 1 failures first, and then finally the yth success with a 1/6 probability. Right, so the probability of the random variable y being equal to 1, the denominator, is going to be what? 5, 6 to the power of 1 minus 1, which is 0, times 1/6. Right, which is what? Which is simply 1/6. And this should be easy for you. I mean, you know that the probability that you obtain a 5 on the first trial is simply 1/6, right? But the denominator is 1/6, so it means that we can just multiply this by 6, right? That's the same equivalent. So 6 being multiplied to whatever it is that we need to find. But before we do that, yeah, actually, so let's leave that 6 there. Let's take the first case when x is equal to 1. So we're going to be equal to what? We're going to equal to times 1, right? We're going to take the x is equal to 1 separately, and we're going to start the summation with 2 after that, right? Because summation is adding, right? So we can take the 1 out, the first case. So 1 times the probability of x being equal to 1, right? Because we're taking the 1 case out, as we just decided, and the y is equal to 1 plus 6 times, and now we're going to start from 2, right? Because we took the 1 out, we're taking the 1 out, so we're going to start the countdown from 2 trials on and on, right? Until infinitely. X times the probability of x equal to x, y is equal to 1. And again, why don't you see the denominator? The denominator is already solved for, right? It's 1 over 6 in the denominator, which gives you 6 outside, right? So we're done with that. So what is this equal to? This tells you that what is the probability that you get a 6 and a 5 on the first trial. There's no probability like that, right? Because you can't have, you're rolling a single die. How would you get a 1? How would you get a 6 and a 5 together on the first trial? Because these are 2 random variables and they're different, right? They're distinct. So the probability of this is 0. There's no way you can get a 6 and a 5 in one trial in the first trial, right? So that's 0 plus this x times probability of x given x, y is equal to 1. Right, so now we just have to solve for this. So now again, I'm going to put a 6 there. I'm going to put x being multiplied. Now what is the probability of this? And again, using using binomial. First, let's solve for the probability of y is equal to 1. We know that's 1/6. And eventually there will be a success for the x random variable, right? Just the same way as it happened for the expected value of x. Right? So eventually there will be another 1/6. Right? But before we put that 1/6, what about the failures first? Don't forget that there are failures involved with that probability. What is going to be the power? Notice that you will have x trials, whatever the x will be, but you're discounting the first trial. Right? So x you have to subtract from x, and not just 1, you have to subtract 2 this time. Because the first trial is already the 5, right? But you're not counting as a failure, right? You're not counting that as a failure because you're starting the countdown from the second trial, right? Based on the nature of what we've done with algebra, right? So x minus 2, because also the last success is also not counted. So you're not counting this and you're not counting that, right? That's why x minus 2 failures. So as a result, these two get cancelled out. You have only 1/6 remaining, right? So it's going to be this to infinity, well, x being multiplied, and then 5/6 x minus 2. So now we can actually write the countdown starting from 1 to infinity, so that we can use the infinite series formula, the convergence formula. And to do that, so if you adjust this and you make it start from 1, you have to adjust the x. You have to add plus 1 if you want to subtract here, right? So it's going to be x plus 1, right? 5/6. Now you're going to add 1, so it's going to be x minus 1. Perfect. And that's exactly what we wanted, right? We're arriving at this conclusion. So we have this x 5/6 x minus 1. I know that you're going to be dealing with 2 terms now, but that's okay. That's okay. That's no problem. Plus 1/6 and that's easy, right? This is going to be just x minus 1. Right, so we know that this is what? This is, again, we already had that term. That's going to be 6, right? That's going to be 6 plus, now what is this going to be equal to? This is typical geometric series, infinite series, that you know converges to 1/6 over 1 minus 5/6, right? That should be clear. You should know that very well. So again, and it's actually interesting because the difference here between this geometric infinite series and this infinite series is that simply you're not squaring this difference here in the denominator. In the first place, you square it when there's an x involved, but when without the x, you're not squaring it, right? So 6 plus 1/6 over 1/6. So that's going to be 6 plus 1 is equal to 7, right? So the result says that you need 7 rolls necessary, the expected value of the random variable x given, right? So the expected value of the number of rolls required to obtain a 6, given that the first roll is equal to a 5, is 7, right? It makes sense. Because you essentially, you're restarting your number of rolls. So the first, you needed 6 rolls to obtain, let's say, a 6 for the first time. But since you already obtained a 5 for the first trial, you're expected to start from the beginning and roll 6 times again. So 6 plus 1, so you will need 7 rolls in total. Right? So that makes a lot of sense. Now the last part requires slightly more work, because now you will get a tougher case. You'll get the expected value of x given that the y random variable is equal to 5. Okay, so let's explore that. So this is written from the first trial, going infinitely, x multiplied by the probability of x being equal to x, given y is equal to 5. So as before, we're going to have this result. So we're going to have x multiplied the probability of x being equal to x to get 1, it's 5, over the probability that y is equal to 5. Okay, so parentheses. Okay, so let's find the denominator first using the notes here. So we already have the notation, right? So we can just use that to find it. Right, so 5 minus 1, right? 5 minus 1, which is 4, multiplied by the success probability, right, which is 1/6. So that's the answer, and it makes sense, right, because the first 4 trials were failures multiplied by themselves 4 times, and then the probability of success. So then we can write this denominator by flipping the fraction, right, because we're essentially having a denominator here. So we're going to flip these two fractions. So we're going to get 6 to the 5th over 5 to the 4th, and same thing, right? X times probability x is equal to x, and y is equal to 5. Okay, doesn't fit, so okay. So now we have to take into account separate cases, and I'm going to work these cases out here. And the separate cases are the following. When it says that given that the necessary number of rolls to obtain a 5 is 5, what is going to be the x, right? And we have to find the expected value. But first we're talking about this part, the probability. So y is equal to 5 all the time. So x can be 4 or less, x can be 5, and we're going to find the probability of that. And x can be 6 and greater, right? So 3 separate cases. And when it's separate, we have to add those respective probabilities. So x is less than or equal to 4. That's the first case. The probability is going to be first noticing that we will have 4/6 probability of not having a 6 and not having a 5, right? This is the failure probability for both 6 and 5. So we're talking about x minus 1 trials when there are failures for these two, right? Now the x trial will be 1/6, and that's where we're going to get the x, right? That's when we're going to get the first 6, right? For the representing the random variable x. But we're not done yet, because we have to also take care of the 5 for the y, right? Next comes the 5/6 probability of not getting a 5. But in order to find the right power, notice that we already took care of not having a 5 for the first x trials. Right? So we have to subtract x trials from 4, like this, 4 minus x. Essentially, because we're and from 4, because x goes up to 4, right? It includes 4 and below. So 4 is going to be the top number, and you subtract the x trials that we already took care of here, both for y and x. That's why this is pertaining to the y as well, the failure, right? So in other words, we already counted the failure for the y along with the failure for the x in this part, 4, 6 to the x minus 1, right? So we have to have 5, 6 now failures for the y, 4 minus x trials, and now finally success for the y, which is 1, 6, right? Which comes on the 5th trial. Next case, x is equal to 5. Now what do you think that's going to be? Basically what it says, is it possible to have a 6 and a 5 on the same trial, right? When the trial number is 5. Can x is equal to 5 and y is equal to 5? No, right? Because you're only having one trial. There's no way that you're going to have two numbers on the same trial, right? You're going to have one face only, so the probability is 0. Now, when x is greater than or equal to 6, the third case, what is going to be there? So here, obviously, first 4 will be neither 6 nor 5. So again, you will have 4/6 probability of not having that, the 6 or 5, right? 4/6 raised to which power? To the 4th, right? Because the first 5 comes on the 5th trial, right? Which is given as 1/6. Next we have what? We have the failure for the x, right? Failures for the x. Now we're going to subtract from x, right? Because the total number is x trials, right? We're going to subtract from x, but how much do we subtract? So we subtract already 4, we subtract already 1, so that's 5, and we also subtract the success for the x, which is the 6th one, right? So x minus 6, right? Because the last one will be a success. So notice this, 4, 5, 6. That's why it's x minus 6 for the failures when it comes to having a first 6, representing the random variable x. Excellent, so you just found 3 separate cases, you're ready to roll. So this will be 6 over 5 to the 4. So what are we going to have? From the 1st to the 4th roll for the first case. We have this. I'm just copying this down. Minus x, and then 1/6 plus 0. So I'm not going to write this because this is the second case, it's 0, so we can disregard it. We can just add this one, plus, and now we're going to start from 6, right? Because when it comes to 5, it's 0, so we can start the 6, just in case you think, why am I skipping the 5 for the x? Because the probability is 0. 6 to infinity. So that's going to be x 4/6 to the 4. Copying this. 1/6 5/6 to x minus 6 and 1/6. Excellent. Okay, hopefully I will have enough room to do some algebra. But basically, what you're going to have is this. So I'm going to simplify. I'm going to simplify, get rid of these two 6s. I would have this 6 to the 3, 5 to the 4. Better rewrite this. So 1 times, right, because we're starting from x is equal to 1, we're going to count, so we're going to have 4 terms representing this, right, because of the summation from 1 to 4. The first term is this, and check this. You have to know how to work summation. I can't show it to you in this video because I'm going to run out of room, so you should do this by yourself. But this is the second term of this part. The third term. And the last term. Okay. And finally, we can start from 1 for the x count. Right? We can start from 1 for the x count. Let me see what that's going to be. That's going to be 4 to the 4. I'm going to take 4 to the 4 out. I'm going to take 5 to the 4 times 6. 5 to the 4 times 6 for this part. I'm going to start from 1 to infinity, right? But remember, if you subtract 5, you have to add 5. So you will get this. X plus 5, 5, 6, x minus 1. Right? So I simplified. And again, I added 5 to get x minus 1, right? Because we subtracted 5 from here. So now, I'm not going to go into deep algebra, but if you do the algebra right here, you should get this. 821 over 5 to the 4 plus 4 to the 4 over 5 to the 4 times 6 from 1 to infinity x minus 1 plus 4 to the 4 over 5 to the 4 times 6. Well, there's another 5 involved, right? Oh no, actually no, we don't have to involve the another 5. From first to infinity x 5, 6, x minus 1. Right, so if you do this right, and I'm not gonna you should be able to do this. You'll have something like this. Notice that 5 to the 4 can be taken out because it's the common factor, right? I'm taking this out. So we'll have 821 plus, and this is infinite series, right? So we will have 36, right? Just as we had in one of the examples, there was a 36. Oh, there was a 36. See, I'm just copying this down. This would be 36, this part, right? So it's 36 over 6, same thing. And then plus 4 to the 4 times 5 over 6. Over 6 times, I should not have had an x here. That's where I made a mistake. You see, x is only for the first term. The second term is just 5, right? So it's just 5. That was my mistake. Let me see. Yeah, there was no x here. That's why I'm thinking that's a different geometric series needed. So I'm going to erase that x. Right, now it makes sense. Right, now it's easy. So this part is just what? That's just 1 over 1/6. Right? This is the geometric series that converges to 1 over 1/6. If you don't count this term that we already wrote here, right? So 1 over 1/6 is 6. That's just that, right? So guess what happens? If you do the algebra right, you should get this answer. 3637 over 625. So that is exactly the expected value of the x random variable given that the y random variable is equal to 5. This is about 5.8 something, right? So nearly what it says is, given that the number of rows necessary to obtain a 5 is 5, right, the expected value of the number of rows necessary to obtain a 6 is about 5.8, right, which makes sense. That's almost 6 rows. Thank you so much for watching. Hope this was helpful. See you in the next video.